Hello and welcome back. In the last video, we uncovered this nice alternate formula for the dot product that just involves arithmetic, and we don't need the angle theta in order to compute it. Right? So we have two forms of the dot product, and as I mentioned in the last video, this gives us a lot of power if we have two different expressions for the dot product. In particular, I can isolate cosine of theta. Everything else is manipulable. I can isolate cosine of theta, and this gives us a way to compute the angle between two vectors. Remember, theta is the angle between u and v. So theta is the angle between these. Remember that theta is always between 0 and pi. You can always choose the angle to be between 0 and pi. Okay, so let's go through that arithmetic. I'm going to solve for cosine theta here. So cosine of theta then is u1 v1 plus u2 v2. So we have that way of computing it. So I'm going to write it as u dot v over magnitude u times magnitude v. So keep in mind, u and v are, again, they're vectors. I'm taking their dot product up here. Down here, I'm taking the magnitude of u and multiplying that by the magnitude v. So we actually have two different kinds of multiplication going on here in this formula. I want you to remember that we have different, these quantities can represent different objects. U and v are vectors. Magnitude u, magnitude v, these are scalars. So up top we have vector, the dot product. Down below we have scalars multiplying with each other. Multiplication of two scalars. And that gives us cosine theta. If we want the angle from this, we can say theta is, the inverse cosine of u dot v over magnitude u times magnitude v. And that gives us our angle between them. So that is pretty nice, but I just want to focus here on cosine theta. I like this form because I know that cosine theta with theta between 0 and pi, cosine theta equals 0 if and only if theta is equal to pi over 2, again, so long as my theta is between 0 and pi. And this theta being pi over 2, this means that, so this is true if and only if u and v are perpendicular, or as we say in 3 dimensions, orthogonal. So this is perpendicular. So in 2 dimensions, you can think perpendicular. So that would be like u going like this and v going straight up, angle of pi over 2 between them. So something like this. So as we can detect right angles with this. Right, so that's one big deal. We're more on that in a second. I do want to jump over to magnitudes with the dot product. What happens when we compute the dot product of a vector with itself? So that is, we take a vector u equal to, let's say, u1, u2, u3. And let's take the dot product of it with itself. Well, then u dot u, as we know, we multiply the components, so u copied twice, so I would get u1 squared plus u2 squared plus u3 squared. And you should recognize this as the square of the magnitude of u. This is the same as magnitude u squared. And this makes sense. I can actually recover this again. We know u dot u is also magnitude of u, magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. But if they're the same vector, then the angle between them is 0. Right, so theta would be equal to 0 here. And cosine of 0 is 1. And so this is magnitude u times magnitude u, or magnitude u squared. So I can recover this 2 different ways using both of the forms. Regardless, this is a pretty nice identity that magnitude of u squared is exactly u dot with itself, u dotted with itself. That's a way to get a hold of magnitude, and at least shows the connection between those two. In a way, dot products are like a square root of the magnitude, only that we can take two vectors and do it. So interesting connection there. Okay, back to this idea of angles between them. I mentioned that this is a way to detect when two vectors are orthogonal. In particular, if I have two vectors u and v, and again we'll use this. I have them up here. Yeah, with u equal to u1, u2, u3, and v equal to v1, v2, v3. Sorry, I'm jumping up and down a little bit here. I mentioned that cosine of theta is 0 if and only if theta is pi over 2. So, and this is if and only if. So if two vectors are orthogonal or perpendicular, then the cosine of theta is equal to 0. And in this case, then, that means u dot v, because magnitude u, magnitude v, these are going to be positive quantities. That means that u dot v must be equal to 0, if and only if. So we have this connection. U and v are perpendicular or orthogonal in 3 dimensions if their dot product is 0, and rather if and only if, computing their dot product. So that is two vectors u and v are orthogonal if and only if u dot v is equal to 0. So if I take two vectors, I compute their dot product, it turns out to be 0, I know they're orthogonal, and vice versa. If I know two vectors are orthogonal, then I immediately know what their dot product is going to be. It's going to be 0. So this is a nice detection method for when two vectors are orthogonal. Oops. Whoa. I don't know what happened there. Okay. This is a way to detect when two vectors are orthogonal. This is going to turn out to be theoretically very helpful, and I don't mean like possibly very helpful. I mean like in the theory of vectors, this detection is going to be very helpful for working out the theory. So this is pretty cool. I can detect when two vectors are orthogonal by computing dot products. I can also detect if two vectors are parallel using dot products. So I'm going to jump up here again. I know that u dot v, if the two vectors are parallel with each other, then theta is, let's say, parallel. Parallel, u and v are parallel, u and v are parallel. If and only if theta is equal to 0 degrees, or possibly if it's going in the opposite direction, if the two vectors are going in the opposite direction, they'd still be parallel. Remember what parallel means? That just means that they're constant multiples of each other. Scalar multiples of each other could be negative. Or theta is 180 degrees, which is pi, 180 degrees. So this would be 0 radians or pi radians. And in this case, then, if that's true, this would mean that cosine of theta is either 1 or negative 1. So cosine theta, then, is equal to either plus or minus 1. And therefore, the dot product between them, so u dot v is uv cosine theta. Cosine theta is either plus or minus 1. I'm looking up here now. That means that u dot v is either plus or minus magnitude u times magnitude v. So if it's either plus or minus that quantity, I know that the two vectors are parallel with each other. And by the way, this goes in the other direction as well. If either of those two things happens, I know cosine theta is either positive or negative 1, and therefore the angle between them is either 0 or 180, and therefore the two vectors are parallel. So again, it goes in two directions. Two vectors are parallel if and only if u dot v is plus or minus the product of their magnitudes. So this is a nice, consequence of this dot product operation, which again came from work that now we've extended, we've abstracted past work, past the physical example, and now it allows us to get information about how the two vectors u and v relate to each other. In particular, we know if they are perpendicular to each other by computing a dot product, we know if they are parallel by computing a dot product, and those are really specific instances of using the dot product to find the angle between the two vectors. So very powerful. I guess I'll just say that's the end of the video. I'll see you next time.